Okay, so hello everyone, and welcome to the third day of the QBrazil Entangling Workshop. Um, so today we're going to be going over quantum operators, but as Arthur mentioned, um, the okay, sorry, wrong workshop. So as Arthur mentioned, there are certain assignments here on Canvas that you're supposed to do. So there's one for each day, and it opens up after the day session, and you're going to have 2 weeks to complete it. So attempt to get at least 10 from each assignment and 75% overall to get the certificate. And each assignment has 3 attempts. So you have just 3 attempts, and the highest score will be picked. So not the average, the highest score will be picked. Okay, so on to our content for today. So before I even jump into the content for today, I'll just do a brief recap on a couple of things we covered yesterday. Okay, so yesterday we introduced quantum systems, and we had an experiment where we had a photon source, a beam splitter, and our photon could either be reflected or transmitted. So we drew some similarities between what was going on in the experiment to the act of tossing a coin. So we said our photon can be the coin, the beam splitter will be the act of tossing the coin, and if our photon is transmitted, that would be the same as our coin landing on head, and if it's reflected, that will be the same as our coin landing on tail. So our beam splitter is going to be a fair coin toss where there's an equal probability of it landing on head and tail. So we looked at an experiment where we tossed our coin twice in a row, and every single time it landed on head. So we said our quantum system deviates from what we understand classically, and we said we're going to explore this quantum system. So we okay. So we started off by looking at the Hadamard operator, and we said the Hadamard operator can be thought of as flipping a fair coin. So the Hadamard operator does the same thing as flipping a fair quantum coin. So we have the 0 state here to represent our coin facing head, and we went on to execute a circuit that simulated tossing our coin. So here we have a single qubit. So a qubit is the quantum version of what a bit is. And here we have a bit, a classical bit, and we've introduced these to our circuit. So the initial value stored in, or the initial state stored in our qubits is going to be the 0 state. So when we initialize our circuit, all our qubits starts off in the 0 state. And now we apply the Hadamard operator, which is our coin flipping operator. And then we measure, that is, we read out the results. So so this is the circuit for the experiment. Okay, so we repeated this a couple of times, 10,000. So we toss our coin okay, so this circuit, if we're describing it as the act of tossing our coin, we set shots to 10,000 here. That means we're going to repeat our circuit 10,000 times, or we're going to toss our coin 10,000 times, and it landed on head a certain number of times and on tail a certain number of times. So the distribution is distribution is 50-50, and because it's probabilistic, it deviated a bit. And we even tried out the third experiment where we toss our coin twice in a row. So if we are to check the results for this, every single time our coin landed, it landed on head. Okay, so we have the 0 state here and the 1 state. So these are vectors. And we've also said we can think of the 0 state as our coin facing head and the 1 state as our coin facing tail. Then went on to look at the NOT operator. So this works exactly the same way we would think of it in the classical sense. So if we are to apply this to the 0 state, we're going to get the 1 state. And if we are to apply this to the 1 state, we're going to get the 0 state. So here we have the Hadamard operator, which is our fair coin flipping operator. So if we are to apply the Hadamard operator to the 0 states, there's supposed to be an equal probability of it landing on head and tail. But if we are to look at this or this matrix, it's different from what we described probabilistic operators to be, because the columns, they don't sum up to 1, and we have a negative entry here. Okay, so at this point, we're applying the Hadamard operator to the 0 state, and this is what we get. So although the results we get from this experiment are exactly what we would expect in a classical experiment also, the entries here, they don't align with how we described our probabilistic states. So the first entry here, we have 1/√2. But if we are to describe a classical system whereby the probability of an outcome is 1/2, we just write 1/2 there. So here we have 1/2 to represent the probability that it lands on tail. But in the quantum state that we're describing here, we have 1/2, even though the probability that it lands on head is 50%. So the entries we have here, they aren't directly the probability values. We have the amplitude here, and it's when we square these that we get the actual probability. So we defined this as the plus state. So when we have this, when we apply the Hadamard operator to the 0 state, we get the plus state. And when we apply the Hadamard operator to the 1 state, we get the minus state. So the notation you see here, for representing quantum states, we call it the Ket notation. So what we have here, V, is a column vector. And so what we have here is a column vector, but we can also represent this as a row vector. And to do that, we just represent it in this form. So we call this a ket, and we call this, oh, sorry, I did exactly the same thing. So we call this ket, and we call this bra. So bra here is a row vector, and the ket you see here is a column vector. So we can actually multiply this. We can actually multiply these. So we'll be taking the inner product. And we'll be taking the inner product. And if we are to do this, we'll be calculating the norm, or the length of the vector. Okay. Then we went on to visualize quantum states. And we said, okay, if we have a quantum state, if I had a quantum state in a single qubit, it's going to be a two-dimensional vector. And the entries here. Okay, so first of all, we said the length of the vector is 1. So this is a unit circle, and the vector will have a length of 1. So the horizontal component here will be A, and the vertical component will be B. And we can also set an angle here. So from this, we can say A is exactly the same as cos theta, and B is sin theta. So for any angle we can set here, we have a valid quantum state. So by changing or varying our angle, we're going to be moving along the circumference of the circle, and any point we pick out is going to be a valid quantum state. And then finally, we looked at superposition and measurement. So for superposition, we just have a linear combination of two states. Or for superposition here, we have a linear combination of our two basis states. And so we have the 0 state and the 1 state here. And there is, okay, so the 0 state has its amplitude, and the 1 state has its own amplitude here. And we've And the amplitudes represent the probability that we get the zero state, for example. Okay, so the amplitudes, when it's squared, we'll get the probability that we get the zero state if we're to measure it. And for the amplitude of the one state, if we're to square it, we get the probability that we okay, sorry, my network is a bit unstable. Okay, but I think it's better now. So for the zero states, it has an amplitude. And when squared, we get the probability that if we are to measure this state, we're going to get the zero state. And similarly for the one state, it has its own amplitude, whereby if we are to square the value you see here, we're going to get the probability that if we are to measure the state, we get the one state. So this is a state in superposition because there is some probability that we can get the zero state, and there's some probability that we can get the one state if we are to measure it. So for the, okay, so applying the Hadamard operator to the one state also, we also get a different superposition state here. And then we looked at interference here. So we applied the Hadamard gate once more. So we applied the Hadamard gate. Once we applied the Hadamard gate to the state you see here. And from there, this is what we get. So we applied the Hadamard operator to the state you see here. That's what we're doing here. And it's a linear system, so it's distributive. And when we applied H to the zero state, this is what we get. H to the one state, this is what we get. But the coefficients of the zero states, they are positive values. But for the one state, we have a positive value here and a negative value here. So these cancel themselves out while these reinforce themselves. So we just add these and we get a 1, while these will cancel themselves out. So this is constructive interference, while this is destructive interference. And this is why when we applied H twice in a row, we always ended up with 0 or with head. So the one states, they ended up canceling themselves, while for the zero states, we just summed the coefficients. And when we're creating quantum algorithms, this is what we're going to be aiming for, whereby what we're interested in finding ends up interfering constructively, while everything else interferes destructively, such that if we are to measure, there's a high probability that we get what we're interested in. So for measurements, we can have a state in superposition. So there's some probability that when we measure, we end up with the 0 states, and some probability that when we measure, we end up with the 1 state. But when we actually measure, we just end up with one or the other. So if we are to measure this, we could just end up seeing the 0 state or the 1 state. So for our quantum states, we can't directly retrieve what's okay. So for qubits, that for the qubits that store our quantum states, we can't directly retrieve the states stored in our qubits. So we measure, and when we measure, we get classical values like 0 and 1. And from these, we create some probability distribution, and we try to reconstruct what the quantum state initially was. Okay. Okay, so I think that's pretty much what we covered yesterday. I'll just jump into the content for today now. So we've already seen the general form for the quantum state in a single qubit. We've already seen this. So, and we've said that by applying operators, we want to change the values of, by applying operators, we want to change the states in our qubit. So in the case here, we can apply an operator to change the angle here, theta. So we have theta within this range, and it's periodic. So even if we go across this, it'll be exactly the same as just starting all over from 0. But by applying our operators, all we're going to do is we'll just end up changing our value of theta here. Okay, so we have a quantum state here, which is the plus state. And theta here is pi over 4. And we even have the minus state. So for the minus state, we have an angle of minus pi over 4 for the minus state. So the angle between the 1 state and the minus state is 3 pi over 4. Okay, so as I was discussing quantum operators earlier, I said what we're aiming to do, or what happens when we apply our quantum operators, is that we end up changing the value of theta here. And one way we can do this is by applying a rotation operator, in this case, the RY gate. And by doing that, we just rotate from one location to another. And obviously, our value of theta would have changed. So we're going to look at a circuit here that will utilize the RY gates. So for the RY gates, this is how we utilize it in our circuit. So this is our quantum circuit, and we're saying we want to perform some rotation with the RY gates. So the first thing that goes here is the angle we want to rotate by, and then we specify the qubits that we're performing the rotation on. So the angle you see here, so it's written angle of rotation, but we're multiplying it by 2. And that's because right now we're using the unit circle to visualize our quantum states. And for the unit circle, the quantum states that we're visualizing only the quantum states that we're visualizing are made up of real values. So the entries in the vector are they are just real values. But in a generalized case, or in a more general form, A and B actually are complex numbers. So we in a general case, they aren't just restricted to real values. And if that's were the case, okay, so when we have the complex values as entries in our quantum state, or the quantum state for a two-dimensional quantum state, we can use a different we can use something else to visualize it. And in that case, we can utilize the block sphere. So the block sphere is a 3D object that we can use to visualize a quantum state that consists of complex numbers. And for the block sphere, the angles are twice what they are in the unit circle. So if I have an angle in the unit circle, the block sphere is going to have twice that angle. If I have an angle between two states in the unit circle, the block sphere is going to have twice that angle. So for example, here, between the 0 and the 1 state, we have pi over 2. But on the block sphere, the angle between them is pi. So that's why we're multiplying by 2 here. So Ry, we're specifying angles in the block sphere instead of the unit circle. So sorry, like I didn't even plan on talking so much about the block sphere. So don't bother too much about complex numbers and the block sphere right now. The main thing I was just trying to say was that here we're specifying angles that are twice what they are on the unit circle. Okay, so now we can utilize the Ry gate in our circuit. So this is the angle we want to rotate by 2 pi over 3, or 120 degrees, I think. So this is the angle we want to rotate by in the unit circle. But now we have our quantum circuit. We're making use of the Ry gate, and we've specified the angle we want to rotate by. So we'll multiply this by 2, and this is the qubits that we're going to perform the rotation on. And finally, we can measure. So if we are to do this, we've set short to 8,000, and we get our counts. So here, as you can see, the probability that we measure 1 is quite high as against measuring 0. So if we are to come back to the circle, so when we initialize our circuit, our qubits starts off with the 0 state, and now want to rotate by 120 degrees, or 2 pi over 3. So we might end up somewhere, let's say here, for example. Let's say we end up here. As you can see, okay, this is meant to be a straight line. I apologize for this. But the state you see here, it's closer to the 1 state than the 0 state. So for this, that's why there is a high probability that we measure 1 as against 0. So we even so this is the quantum state we get after we've performed the rotation. So we have minus 1/2 and 2, okay, I can, and 0.866. I think this is root 3/2. Yes, this should be root 3/2. So if we are to go back to the circle, so here, we have 60 degrees. And if we are to calculate the horizontal and vertical components, so for the horizontal component, we get 1/2, but this is along the negative axis. So this is minus 1/2. So we just calculate cos 60. We calculate cos 60 and we get minus 1/2. And if we are to calculate sine 60, we're going to get root 3/2. And those are the values that we just saw below. Okay, so we have a task here. And okay, so let's try out the task we have here. So we're to randomly pick an angle within this range, and we're to make 1,000 copies of the quantum state we get from this angle and measure each of them. So what are the expected numbers of observing the 0 and the 1 states? Okay, so I guess the task we have here doesn't have a definite solution. So this is something you can just try out. You can just try out utilizing the RY gates and measuring to see the results. So I'll move on to the next notebook. Okay, so so we've been speaking about rotations as we've been discussing our quantum operators, but let's look at rotations in a bit more detail. Okay, so I have a question for the chat. We start off in the 0 state and we perform some rotation and we end up in the plus state. So if we are to repeat this rotation 5 more times, where do we end up? So we start off in the 0 state, we perform some rotation, and we end up in the plus state. If we are to repeat the same rotation 5 more times, where do we end up? Someone said 5 pi over 4. Wow, that's a nice answer. Pretty straightforward. Just multiply this with 5 and yeah, that's actually correct too. Oh no, it's not. I said 5 more times actually. So we performed this the first time, and if you did 5 more times, where do we end up? So you should have multiplied by 6 instead. Okay, so I'm seeing the -1 state. And yes, that's where we end up. This is exactly where we end up. So if we keep performing the rotation, these are all the states that we're going to visit. So we'll start off in the 0 state, and when we apply the rotation, we end up at the plus state. We apply it once more, we end up at the 1 state. We apply it again, we end up, I think, -1. No, sorry, minus, minus, then -0, minus plus, -1, and then the minus state, and then we start off from 0 again. So we just keep hopping between these states repeatedly if you keep performing the rotation. So this is the matrix for the rotation that was performed here. So it looks similar to the Hadamard operator, but the minus sign is at a different location. Okay, so we have a task here where we're to perform the rotation 7 times and draw each state that it passes through. Each time we apply it. So let's look at the solution. So we start off on the 0 states. Okay, so we've spoken about this, but these are all the states that we're going to visit. And I think at the 7th time, this is where we stop. So we have the general form of the rotation matrix here, where we can just specify the angle we want to rotate by. So in the matrix you see here, by specifying the angle theta, that will be the angle that we're going to rotate by. So if we have a quantum state, so let's say the initial location of our quantum state is at the location phi. And then, so the initial location of our quantum state is at the angle phi. And we're going to perform some rotation by the angle theta. So we're to multiply these. And if we are to do this, we're going to get cos theta cos phi minus sine theta sine phi. So minus sine theta sine phi. And below, we have sine theta cos phi. So sine theta cos phi. Sine theta cos phi plus cos theta sine phi plus cos theta sine phi. So from what we have here, we can, this is one side of a very common trig identity. So we can rewrite this as cos, so I'll just start off with this. I'll write phi first, cos phi plus theta. And then below, we can write sine phi plus theta. So from what we have here, all we're doing is adding theta to phi. So we said we want to perform a rotation. And so we want to perform a rotation, and if the initial location of our quantum state is phi, okay, so we performed the rotation, and now we end up at theta. So as you can see, all we're doing is adding the angle theta to phi. So when we utilize this matrix, all we're doing is adding theta to the quantum state we're applying it to. And would have successfully rotated to a new location. Okay, so let's take a look at task 6 here. So we're to randomly pick an angle within this range, and we have 2 separate qubits, which are initially in the 0 state. So for the first qubit, we're going to rotate by the angle we picked within this range. And for the second qubit, we're going to add pi over 2 to that angle and rotate by what we get from the sum. So if we are to do this, okay, so if we are to do this, we just implement this and check the dot product for the 2 states we get. So let's see what happens here in task 6. So we've randomly picked our angle, and then okay, so initially we picked it in degrees, then we convert it to radians. So for the first angle, it's what we randomly picked, and for the second, we just add pi over 2. And now we can introduce, okay, so now we have our quantum circuit with a single qubit and a single bit. And then in our circuit, we're going to utilize the RY gates, or we're going to apply the RY gates on our qubits with the rotation angle that we randomly selected. And then we retrieve the results. And we also have a second circuit here where we're using the second angle instead. Okay, so with the state vector simulator here, instead of measuring, we're just going to retrieve the actual quantum state. So like behind the scenes, we're probably still going to measure and reconstruct the quantum state, but this just abstracts the whole thing for us. So if we are to do this and calculate the dot product, we're always going to get 0. And that's because we have 90 degrees between the two angles we selected. So the two vectors are orthogonal, and the two vectors are perpendicular. So the dot product is going to be 0. Okay, so finally, let's look at task 7 here before we move on to the next notebook. So we randomly pick an angle again, and then, so here, instead of adding, we're going to subtract pi over 2. And then we're allowed to perform one more measurement before, we're to perform one more rotation before we measure. And from the results we get, we should try and decide which of these two angles we rotated by. Okay, so we have a circle. Okay, let me just put the axis first. So we have a circle and we randomly pick an angle. So let's say the angle we pick, it's somewhere like here, for example. So we randomly pick an angle here. And then we subtract pi over 2. So we end up somewhere like here. And we're allowed to do one more rotation before we measure. We're allowed to do one more rotation before we measure and decide which of these angles we picked. Okay, so let's say the so let's say the angle we picked was the plus state. So if we are to subtract pi over 2, we're going to end up at the minus state. And then if we are to perform one more rotation before we measure to help distinguish these two angles, let's say we are to rotate by pi over 4. So if we are to rotate by pi over 4, so from the plus state, rotating by pi over 4, we're going to end up at the 1 state. And then For the minus state, rotating by pi over 4, we're going to end up at the 0 state. So if we are to measure, if we see 0, then we know it's theta2 that we chose. But if we see 1, then you know it's theta1 that we randomly chose between these two angles. Okay. So from the circuit here, we randomly picked our angle. We've calculated the two possible angles we can rotate by and have our circuit. And we're going to choose between these two angles, the one we're going to rotate by. Okay, so okay, sorry. I guess I made a mistake. What I was describing. But here we rotated by the angle we initially chose in the reverse direction. So if we are to measure the 0 state, then we know that it's if we are to measure the 0 state, okay, so let me just my diagram. Okay, so let me discard this and discard this. So here we chose the plus state initially, and when we subtracted pi over 2, we ended up on the minus state. So we randomly picked between one of these, and we're trying to figure out which of these we chose. So we're to perform some rotation, then measure to differentiate these. So if we are to rotate by minus theta, or minus the rotation angle we initially chose, the plus state here will end up at 0, and the minus state will end up at -1. So if we are to measure and we see 0, then we know it's the rotation angle 1 that we initially chose. But if we are to measure and see 1, then we know it's the rotation angle then we know that the rotation angle was rotation angle 2. Okay, so let me check. I think I have a couple of questions. Okay, yeah, sure. You can post your question in the chat. Okay, so let's move on to the next notebook. Okay, so I'm going to provide a circle once more. And so we're introducing a new operator or gate here. I don't think we've come across the Z operator yet. And if we are to apply the Z operator if we are to apply the Z operator to the 1 state, or let me write it like, okay, yeah, let me write it like this. If we are to apply the operator to the 1 state, we're going to get the -1 state. we're going to get the -1 state. So this is the matrix for the Z operator. So we have the 1 state up here. We have the 1 state. And below here, we have the -1 state. Okay, so here we have 0 and -0. So if we are to apply the, okay, or better put, if the Z operator is okay, so thus far we've been talking of rotation operators. And what do you think the angle of rotation for the Z operator will be from this? Or it's a terrible question. I'm thinking of how to properly phrase it, but it's not just coming to me. What do you think the rotation angle for the Z operator is? Any takers? So we have the 1 state, and we applied the Z operator to the 1 state, and we got the -1 state. So what do you think the angle of rotation for the Z operator is? Or if you think the Z operator is a rotation operator, what do you think its angle of rotation is? What do you think its angle? Okay. Okay, so I'm saying pi. Okay, so next question. Do you even think, to begin with, that the Z operator is a rotation operator? So is the Z operator a rotation operator or not? Okay, so I'm saying no, no, no. Okay, so let's see. Here we said we've applied the Z operator to the 1 state, and we got the -1 state. So if we are to perform some rotation, we'll start off with 1, and we're going to rotate by pi to end up at -1. But from the matrix you see here, let's say we applied the Z operator to the 1 state instead. Sorry, the 0 state instead. If we are to do this, we're still going to end up with the 0 state. So we would have not rotated by any angle if we're applying the Z operator to the 0 state. So this obviously won't make sense. Like, why do we apply a rotation operator to the 0 state and it stays the same, or it rotates by 2 pi, whereas for the 1 state, when we apply it, it rotates by pi? Because if it's a rotation operator, the angle you rotate by should be consistent. So talking of the Z operator as a rotation operator doesn't make much sense here on the unit circle. So right now we're looking at reflections, and some operators aren't rotation operators on the unit circle. They are reflection operators. So here, our line of reflection is the x-axis. That's okay. So our line of reflection is x-axis. So if the line here was a mirror and the vector you see here was the one state, if we are to reflect it, we're going to get an image of the one state below, which is going to be the minus state. But if the x-axis is our line of reflection for the zero state, so we have the zero state here on this line. If we attempt to reflect this, we're still going to stay on the same line. So because the zero state is on the line of reflection, its state won't change when we apply it. So let's take a look at a couple of more reflection operators. Okay, so this is the Z gate, which is what we just saw. And we said the line of reflection is the x-axis. So if we start off here and we reflect this, then we get U prime. And if we apply our operator once more to U prime, then we end up back at U. So we're just going to be alternating between these two states if we keep applying the Z operator. So the Hadamard operator is also a reflection operator. And when we apply the Hadamard operator to the zero state, we get the plus state. And if I were to apply to the plus state once more, we're going to get the zero state. If I apply to the one state, we get the minus state. And if I apply to the minus state, we get the one state once more. So what's the line of reflection for the Hadamard gate? So if you know, you can type in the chat. What's the line of reflection for the Hadamard gate? What's the line of reflection for the Hadamard gate? So if we have the zero state, we end up at the plus state. And if we have the one state, we end up at the minus state. So what's the line of reflection for the Hadamard gate? If you know, you can type in the chat. Okay, pi over 8. Pi over 8. Okay, so pi over 8 should be somewhere around here. Okay, perfect. So I think here if we are to reflect about this line, so 0 end up at plus, plus end up at 0, 1 will end up at minus, minus end up at 1. So let's scroll down and see the solution. Okay, yes. The line of reflection is actually pi over 8. So thanks, Cairo and Manuel. Thanks. So this is the line. This is the line of reflection for the Hadamard operator, pi over 8. So which operator has this line of reflection? Which operator has this line of reflection? Does anyone know? Okay. You can type in the chat which operator has this line of reflection. Okay, so I'm seeing the most common suggestion here is not. So thanks, Nicholas. Thanks, Manuel. So sure, the line of reflection for this line, y is equal to x, it's actually the x gate or the not operator. So if we are to look here, so this is the line of reflection. So if we start off with the 0 state, we're going to end up at the 1 state. If we start with the 0 state, we're going to end up at the 1 state. And if we start off at the 1 state, we're going to end up at the 0 state. If we have the plus state, nothing is going to happen. But let's say we had the minus state. If you have the minus state and we apply the not operator, we're going to end up at the minus state. The minus state. So for so let's say for the 0 operator, if we apply the x gate, we're going to swap these values. So if we apply the x gate to the 0 operator, we'll swap these values, and we're going to get 0, 1, which is the 1 state. So clearly this works for the x gate. And if we are to apply the x gate to the plus state, so we have 1 over root 2, 1 over root 2. So in this case, if we are to swap these values, we're still going to get 1 over root 2, 1 over root 2. So nothing happens because the plus state is on the line of reflection. Nothing is going to happen. The value is going to stay the same. And finally, if we are to apply the x gates to if I were to apply the xk to the minus state, okay, I should have even simplified my work by leaving all that. Okay, so here we have the minus state. If you are to apply the xk to the minus state, we're going to swap these values. And so the minus sign is here. We're going to swap these values. And this is definitely the minus minus state. So these are a couple of reflection operators and the line of reflection for each one of them. So here we have the matrix representation for reflection in general, where theta here represents the line of reflection. So theta here represents the line of reflection for this matrix. And if we are to apply it to a quantum state, let's say cos phi sine phi. So cos phi sine phi. We're going to get cos 2 theta minus phi, and then sine 2 theta minus phi. So this is what we get if we are to apply the matrix you see here to this quantum state. Okay, so from what we have here, so this represents reflection. So when you see something like this is reflection, because imagine we had the state phi here. So imagine we had the state phi here, and theta here is our line of reflection. So let's say the line of reflection for theta is pi over 2. For the y-axis. So this is our line of reflection. If we multiply this by 2, so this is our line of reflection. But if we multiply theta by 2, then this will become our line of reflection. And then if we subtract phi from this line, so this line has pi, and this line, the line of reflection for this line, the angle for this line of reflection is pi, and we get that by multiplying theta here by 2. So if we have this as our line of reflection, or from this line, if we are to, sorry, I keep calling this line of reflection, sorry. This is not line of reflection. This is our line of reflection, theta, which is pi over 2. But if we are to multiply this by 2, then we're going to get the line you see here. And then, or instead of calling it a line, So if you are to multiply this by 2, we'll end up with a state at this location. So if we subtract phi at this point, so if we subtract phi at this point, or no, let me make this as close as possible. If we subtract phi at this point, we would have successfully created a reflection of the state you see here about this line. So this is our line of reflection, and by multiplying theta here by 2 and subtracting phi, we would have successfully created an image of the initial state about this line. Okay. So I think that's pretty much everything here in the reflection notebook. So let's move on to the next notebook on quantum tomography. Okay, so for quantum tomography, so for quantum tomography, so I think tomography comes from some imaging procedure, some medical imaging procedure. I think where you're trying to reconstruct an image from data you've gathered. Okay, I'm not going to even claim to be an expert at tomography or even to properly understand what it is, but it has something to do with like reconstructing an image from I think probably maybe data you've collected somehow. So here in quantum tomography, this has nothing to do with imaging in any way. We're trying to use statistics we've collected from tossing a coin to recreate our quantum state. So that's why I think it was called quantum tomography, because it just has to do with reconstructing something from data I've gathered somehow. So here in the quantum tomography notebook, we're going to be giving 1,000 copies of some quantum state or 1,000 copies of some qubits. So our qubits there's some quantum state stored in our qubits, and we're giving 1,000 copies of this. So we're supposed to figure out what the state in our qubits is just by performing measurements and collecting statistics. So that's the idea behind the quantum tomography notebook. So, okay. So let's look at a case whereby the state stored in our qubits is the plus state. So let's say we had the plus state stored in our qubits. Okay, let's say the plus state stored in our qubits, and we're supposed to figure out. Let's say the plus state stored in our qubits, and we're supposed to figure out the fact that it's the plus state stored in our qubits. Okay, so if I were to, okay, so we're given 1,000 copies, and let's say I was to measure 500 copies. So I measure 500 copies, and from measuring 500 copies, I was so lucky that I got 250 of zero of the zero state and 250 of the one state. Okay, so from this, I know that my quantum state is in an equal superposition. So I know that my quantum state is in an equal superposition. So there's some possibility that it's the minor state also. So if that was the case, that my quantum state was in equal superposition, and there's some possibilities the plus state, there are some possibilities the minus state. Is it possible for me to figure out which one of these states it is? So you can type in the chat. So I had 1,000 copies. I've used 500. I've measured 500, and I got 0 for 250, and I got 0 250 times, and I got 1 250 times. So I can tell from this that, or from this, I can I'll make a guess and say that my quantum state is in equal superposition. So there's some possibilities the plus state, and there's some possibilities the minus state. Is it possible for me to perform, is it possible for me to differentiate, is it possible for me to figure out which one of these states was the initial quantum state? So you can type in the chat if you know the answer. Okay. So I'm seeing some suggestions here in the chat. Someone is saying we apply the Hadamard first and then we measure. Okay, wow, that's a nice suggestion. I'm also seeing do a rotation. Okay, so my question is that we're given a quantum state and we don't know what the quantum state is. We're given 1,000 copies of this quantum state and we don't know what the quantum state is. So we measured 500 of these copies. And when we did that, we got 0 250 times and 1 250 times. So from this, we said, okay, there is a good chance that our quantum state is in equal superposition. So we said there's some possibilities the plus state, there's some possibilities the minus state. At this point, can we tell which of these was, not at this point exactly, but is there anything we can do to tell which of these was the initial quantum states that we were handed or given? Okay, so the question I'm asking is, can we differentiate these? Can we tell which of these was the initial quantum state? So I haven't told you the quantum state that was given. But is there any way you could figure it out if it was a plus state or if there is to figure out which state it was, knowing that it was either one of the plus states or the minus states? Okay, so I'm seeing you can rotate by minus pi over 4. Okay, some people have just made up their minds it's a plus state. Okay, so um okay, someone is saying cannot. Why not minus plus, for example? Okay, so yes, there's a possibility it was a minus plus, but my question was just restricting to just these two states. So yes, the people that said we can apply the Hadamard gate first before we measure. Yes, that's correct. If you were to apply the Hadamard to the plus state, you're going to get 0. And if you are to apply the Hadamard to the one state, sorry, to the minus state, um, we're going to get 1. And if we are to measure, we can differentiate these. Similarly, if we are to rotate by some angle, for example, I think someone said minus pi over 4 or something like that. I can't remember the exact, yeah, minus pi over 4. If we are to do that, the minus state will become minus 1 and the plus state will become 0. And we will successfully be able to distinguish them. So um, okay, so we can successfully distinguish these from what we've just seen. So by applying some gates before we measure. So for the remaining 500 copies, we can apply some gates and then measure, and we'll successfully be able to distinguish these. Okay, so let's even extend the states. Let's add a couple more. So let's add the minus minus states and the minus plus states. So if we're given these 4 states, is there any way we can figure out the initial state that we're handed? So we had 1,000 copies, we measured 500, and we said the we measured and we said our quantum state is in equal superposition. So all these 4 states are in equal superposition. And we said we can successfully distinguish these. So, okay, let me even just cancel out a couple of these since. So we've said we can successfully distinguish the plus state and the minus state by, let's say, applying the Hadamard gate, for example, before we measure. So in this case, that we have like the plus state and the minus plus state, for example. So it could be either one of these because both of these states are in equal superposition. Is there any way we can figure out the initial state that was handed to us? So 1,000 copies of some states. Can we tell which of these it is? So my question is, can you distinguish these two states? So we have two states here, the plus state and the minus plus state. Can we distinguish these states? Okay. Okay, so I can see we can't tell them apart. Okay. I think not. Maybe apply reflection for zero line. For zero line. If we are to apply reflection for zero line, okay, so if we are to apply this reflection, the minus plus state, if we are to reflect, will become the minus minus state. And then the plus state will become the minus state if we are to reflect about the zero line. So we'll still be asking ourselves the same question, but with different states. H, okay, H, let's try H. If we are to apply H to the zero state, we're going to get, if we are to apply H to the plus state, we're going to get the zero state. And if we are to apply H to the minus plus state, we're going to get the minus zero state. So we pretty much have a similar problem. So actually, no. There is no operator we can apply to differentiate two states that are different by, let's say, negative sign in front of them. So the zero states and minus zero, there is no way to differentiate these. There is no operator we can apply. That's when we measure, we're going to differentiate these. Similarly, for plus and minus plus, minus and minus minus, 1 and minus 1, or like, let's say, any quantum state, psi and minus psi. So there is no operator we can apply, then measure, that will help us differentiate these states. So what we have here, it's called the global phase. So this is called the global phase. And for a single qubit, we can discard the global phase because for a single qubit, we can discard the global phase because there is no way we can differentiate states that are different by some global phase. So yes, state X and minus X can be considered the same thing. So for this half of the circle, we're just going to do away with it because all the states in this half can be thought of as a state in the other half with a negative sign. Like for example, we have the plus state here, and then we have the minus plus state here. We have the minus state here, and we have the minus minus states at the other side. So all the states in this half, we can discard this half of the circle because all the states on this half are just states on the other half, but with a minus sign. So we can just utilize the semicircle you see here. So we can utilize the semicircle you see here because all the states on the other half are just some states we have on the right half, but with a negative sign. So okay, so there's some section here on global phase. But that's pretty much everything about quantum tomography. So I think I just like checked out the definition for tomography. So it has to do with using some penetrating wave to obtain sections of the body and reconstruct an image from that. So it still boils down to reconstructing image based on some data I collected. And similarly here, we're collecting statistics about our quantum state, and I'm trying to reconstruct it from the data that we collect. Okay, so let's move on to 2 qubits. So similar to how we saw 2 probabilistic bits, so for our 2 probabilistic bits, we used a tensor product to create some combined system. And we're doing something similar here for our single qubit quantum states. So we have some quantum states A and some quantum state B, and we can take a tensor to combine our 2 states. So so this is like an abbreviated or a short version of this. So instead of having to like rewrite the tensor over and over again, we can just write like A and B here together. So that's why we have 0, 0 here. So this is just trying to say we have some quantum states in the state 0 and some other quantum states in the state 0, and we've taken a tensor. So this is the vector for our quantum state 0, 0. So 1 here is obviously the amplitude for 0, 0. Then 0 here, okay. 0 here is the amplitude for 0, 1. This is the amplitude for 1, 0, and the amplitude for 1, 1. So we have a circuit here with 2 qubits, and we're applying the Hadamard operator to our 2 qubits. So here, we can also take a tensor of our 2 Hadamard gates, and I think we're probably going to see this somewhere else. So if you see something like this, it just means we have 2, or okay, because we have 2 here. So whatever value is written here, so let's say we had n here. So this would just mean we have n Hadamard gates that we're taking a tensor of, or we're taking a tensor of 10 Hadamard gates. So in the case, sorry, because I don't need to explain this. We have two matrices, and when we take the tensor products, this is what we get. So we can even retrieve the operator that was applied in our circuit using the unitary simulator. So as you can see here, so here we applied two Hadamard gates to the two qubits in our circuit. And from this, as you can see, we can just multiply the Hadamard or the 4x4 matrix we got from here. We can just apply that with the four-dimensional vector we get by combining these. Or we can apply the Hadamard gates to the qubits individually before we take the tensor. So here, we combine the gates, combine the states, and multiply it. Here, we applied our operators to our states, then took the tensor after that. And this is just exactly the same thing here, but we're writing this in linear form. Okay, so we've even seen the CNOT operator. And we said that the CNOT operator is a 2-qubit gate. So we can't apply the CNOT operator to a single qubit. Or we can't even apply it to 3 qubits, for example. We apply it only to 2 qubits. And it works such that, okay, so it works with, it works such that if the first qubit here has a value of 0, we're going to do nothing to the second qubit. So if the first qubit has a value of 0, we're going to do nothing to the second qubit. So the first qubit is called the control qubit, and the second qubit is called the target. But if the first qubit, which is our control qubit, has a value of 1, then we're going to apply a NOT operator to the target. So here, our control has a value of 1, and we apply NOT to 0, and then we get 1. Here also, our control has a value of 1, and if we are to apply NOT to the target, we're going to get 0. So in our quantum circuits, we utilize the CNOT operator by making use of the CX kits. So in our circuits, this is our CX kit, and the first thing we specify here is the control and then the target. So the qubits at location 1 is the control, and the qubits at location 0 is the target. So this is our circuit with the CNOT operator. So Q1 here is the control, and Q0 here is the target. And these are the results we get. So because the control has a value of 0, we're going to do nothing. So here, we're applying the CNOT operator to 0, 1. And because the control has a value of 0, we're going to do nothing. So our output stays the same. So it's still 0, 1. Then here we're applying the C0 operator to 1, 0. So because 1 here is the control, we're going to apply the not operator you see here. So we're going to flip the value of the target and get 1, 1. And then finally, for the final circuit here, we have 1, 1. And because our control has value of 1, we're going to flip the target. So the 1 becomes 0. So we now have 1, 0 as our output. So there are a couple of tasks here that you can try out on your own. Okay. So I think the time is almost up. We've pretty much covered everything we're meant to cover for the day. So there's one more notebook here on phase kickback. And for phase kickback, it works such that we're applying a C0 operator, but the control qubit is what changes, not the target. So I'm not going to, I'll just leave this notebook for now. So we'll cover this tomorrow instead. We'll cover this tomorrow instead. But that's the main idea of phase kickback. We're applying a C0 operator or a controlled not operator. And the controller qubits or the control qubits is what gets affected, not the target. So I don't know if there are any questions at this point in time. Thanks a lot for that, Cairo. Thank you. Okay, so I don't know if anyone from the Q Brazil team has anything to add. Chrisia, Letitia.
Nothing to add for this lecture. We'll be maybe waiting a couple of minutes before we start our panel today. But yeah, beautiful lecture today. Really nice. It's always good because I have an opportunity to learn new things that we already know, but in a different way. Really nice.
Okay, thanks for that. I'll be astonished if actually taught you something new, but thanks for the commendation.
Okay, guys. So I stopped recording. We finished.
Yes, we will have the panel in 5 minutes, right, Hans? And
Okay.
yes, could you add the panelists to the
Can you add them yourselves or not?
No, because I'm a panelist.
I will make you panelist. Sorry. I think now you should be able to do it. No? So let me.
2 seconds.
Place.
Okay, I think we should also stop the recording at some point in time, so that for people that just want to watch the panel session,